Hello, I'm Norman Wildberger. In this video I want to talk about some elementary physics, basically high school physics, but I want to look at it from a linear algebra point of view. There are plenty of opportunities for casting some aspects of elementary physics in a way that's conducive to our geometrical way of thinking. We're going to see a good example today. This is also a stepping stone towards us delving into special relativity. All right, so we're going to get a little bit of familiarity with some basic physics from a purely Newtonian point of view, a very classical point of view. So we're interested in some one-dimensional high school level mechanics. So we're just going to be operating in one dimension. We've got particles moving along a line, and basically they're going to be colliding. And we're interested in what happens in a collision. And these are going to be elastic collisions, meaning that energy is conserved. So the idea is we have one particle, say of mass m1, heading this way, another particle mass m2 heading this way, and the relative sizes of these little spheres is supposed to indicate that m1 is bigger than m2. You can think of these as little ball bearings. Okay, and they're heading towards each other with certain velocities. The velocity of this one will be v1, which is a vector pointing in that direction, and the velocity of this one will be v2, which happens to be a vector pointing in this direction. And these really are vector quantities, so they have the direction but also the magnitude. So this longer vector here represents that this m1 particle is moving faster than this m2 particle. All right, so they're coming together like this, with the m1 going faster than the m2, and then they hit, and they kind of bounce, interact somehow. And then afterwards, we might find that the m1 particle is still moving in the same direction, but now at a slower velocity u1, while the m2 particle has bounced back from where it came and is heading back in that direction at some new velocity u2. And a natural question is, if we know the initial gradients, v1, v2, m1, and m2, how do we find the final velocities u1 and u2? So the main concepts here are velocity, mass, momentum, and energy. And we're working in the context of Newtonian mechanics, which is largely driven by Newton's law F equals ma. Okay, so I hope we all remember the formula for the kinetic energy of a particle of mass m moving with velocity v, or more precisely with speed v. So the energy is 1/2 mv squared. That's the kinetic energy. And m here is the mass of the particle, and v is the vector velocity, given as a vector, while v without a hat on it is the length of v, or what's usually called the speed. Okay, what about mass? Well, mass is a very interesting concept, and there are different kinds of ideas about mass. There are in fact three somewhat separate ways of thinking about mass in Newtonian mechanics. One is in terms of its weight. So if you measure a ball bearing by weighing it, you get a certain number. But then there's also sort of its inertia with respect to a force. So if you apply a force to it, what kind of acceleration are you going to get? Well, the proportionality constant is also its inertial mass. And then there's a third kind of aspect where you can think of the mass as exerting a gravitational force on something else. Okay? So those three different concepts of mass more or less coincide, but it's not entirely obvious why they do. It's sort of one of those marvels of classical physics. And let's make sure that we understand what we mean by velocity. So here is our position line, and here's a little particle, and it's moving in this direction. And let's say that at time t1 equals 3, it happens to be at the point 1. And a little bit later on, at time t2 equals 5, it happens to be at the position 4. All right. So the velocity is in general a vector quantity, and it has a direction and a magnitude. And so it fits very naturally with our vector space linear algebra point of view. The usual formula is that delta V is the change in x divided by the change in time. And it's useful for us to think about this change in x as being a difference between two position vectors. So here's the position x1, here's the position x2, and we might think about the position vectors of x1 and x2. So this numerator here is really a difference of position vectors, and so is also a vector. So the numerator is really the vector that goes from here to here. t2 minus t1, those are constants, 5 and 3. So we're just dividing x2 minus x1 in this case by 5 and minus 3. So in this case, it's a one-dimensional vector, which are almost the same as numbers, but we might distinguish them by putting round brackets around the vectors, just as we do for vectors with 2 or 3 or higher components. So that in this case, the velocity is the vector 4 minus the vector 1 divided by the difference in times. So that's the vector 3 times a half, which we could write as the vector 3/2. So that would be the vector, while the speed would be the absolute value of that, which is 3/2. While the energy is a scalar quantity, so the energy of a particle, the kinetic energy, is a number, the momentum is actually a vector. And the formula is P equals m times v, where v is the velocity vector. So here we have the number line, and we have two particles. This one here, with a mass of 30, m1, is traveling from here to here. It's at this position 2 at time t equals 5, and it's at this position minus 1 at t equals 10. Over here we have a bigger particle, represented by a bigger circle or sphere. Its mass is m2, which is 100. And at the same time, t equals 5, it happens to be at position 7, and a little while later at t equals 10, it's at position 11. What are the various momenta? So P1, the momentum of this thing, is the mass m1 times the vector v1. That's 30 times the difference in the x-coordinates, minus 1 minus 2, divided by the difference in times, 10 minus 5. And 30 over 5 is 6, and minus 1 minus 2 is the vector minus 3. So altogether that's the vector minus 18. So it's a vector in this direction of size 18. And what about the momentum of this thing here? Well, it's m2 times v2. m2 is 100. And the velocity is final position minus initial position, 11 minus 7, divided by the difference in the times, 10 minus 5 as before. So 100 over 5 is 20. 11 minus 7 is the vector 4, for a total momentum of 80. In the positive direction, representing a vector going that way. So the momentum of this mass m2 is considerably more than the momentum of m1, and it's in the opposite direction. So both energy and momentum are pretty closely connected because they're both made up of the mass and more or less the velocity, except here's the length of the velocity squared, and here's just the velocity as a vector. So what is the difference? How should we perhaps think about these two things if you haven't thought about physics for a while? Well, let's say that you're an astronaut floating around in space, perhaps like Sandra Bullock in that great movie Gravity that appeared not too long ago. So, and some particle is coming towards you. Let's suppose it's not too big, and it hits you. Then that particle has an energy as well as a momentum. And very simplistically, you can think of the energy as causing some pain. The energy hits you, and you feel an ouch. The higher the energy, the more pain you're getting because that thing is whapping you. The momentum is actually more pushing you than anything else. So that particle is going to give you some momentum. It's going to be transferred depending on the momentum of this thing here. Okay. So if you have the same momentum but different masses and velocities, you can get different energies. For example, if we replace this particle coming in with a particle that was twice as massive but half as fast, then the momentum wouldn't change. But because of the square of the velocity or speed term, the energy would decrease. Okay, it'd be quite less energetic. Conversely, if you multiply the velocity, say, by 2, the momentum is going to increase by 2, but the energy is going to go up by a factor of 4. Right? So it's the momentum that's going to end up pushing you along, and the energy that's going to cause a damage to your spacesuit or your ribs. A little bit simple-minded, but it's one way of thinking about energy and momentum. Now, energy and momentum are both very, very important in physics because of two fundamental conservation laws. So there's the conservation of energy law, which says that in a collision, the total energy, i.e. the sum of the energies, is conserved. If you add up all the energies before and you add up all the energies afterwards, you should get the same. Now, this is a very broad statement that actually includes not just kinetic energy, but also other kinds of energies. Well, there are other kinds of energies like heat energy, vibrational energy, potential energy, and so on. So this law really is an embracing one that covers all kinds of energies. But if we're just considering elastic collisions, so between very hard steel ball bearings, for which there's very little heat produced and very little sound energy, okay, just clack, okay, not very much, then most of the energy that's involved is kinetic energy. And so that's sort of a simple kind of situation where this law is really a law about conservation of kinetic energy. And the other important conservation law that we're going to talk about is the conservation of momentum, which says that in a collision, the total momentum, i.e. the sum of the individual momenta, is conserved. The total amount of momentum before equals the total amount of momentum afterwards. And because these are different kinds of quantities, this is really a law about scalars. We have an equation. On one side you have the total energy before, on the other side the total energy afterwards. Those are two numbers, and the two numbers have to be equal. With this law, the total momentum is a vector before, and the total momentum afterwards is a vector, and so it's really a vector equation that we're talking about. All right, so these two laws are very fundamental in physics, go back to the founders of the subject. I think were identified by Descartes and Leibniz, Newton certainly, and put in a very modern formulation by the great German mathematician Emmy Noether in the early part of the 20th century. I'll mention her a little bit later on. All right, so these are very powerful laws because they identify invariant quantities, things that are unchanged even if we're performing rather complex collisions or other kinds of activities. All right, so physicists like this kind of thing, and they have found many other kinds of conserved or invariant quantities, prominently angular momentum, charge, baryon number, lepton number, spin, and they have various other more complicated things associated with quantum mechanics and particle mechanics. Okay. So these are sort of key laws, though, that hold in a wide variety of situations and are very useful, sort of bread and butter for your working physicist. All right, so let's go back to this main example of an elastic collision that we want to understand. We want to analyze this using a little bit of linear algebra together with these conservation laws. So we have two particles, M1 and M2, have with masses M1 and M2, and they're heading towards each other and they're going to collide. And they have initial velocities V1 and V2. And after they collide, they have final velocities U1 and U2. Now, to make life a little bit simpler, because we're in a one-dimensional situation, we can really take care of the direction just with a plus or minus sign. So we can't do this in higher dimensions, but in one dimension we can get away with replacing the vectors with just numbers. In other words, sign speeds. So not just speeds, but speeds with either a plus sign or a negative sign, depending whether we're going, say, in the positive direction or the negative direction. So if we agree that this is the positive direction, then this will have a positive sign speed and this will have a negative sign speed. So we can talk about just numbers, velocities as just being sign speeds or numbers. And our basic thing that we'd like to figure out is, if we know V1, V2, and M1 and M2, how do we figure out what the final velocities U1 and U2 are? All right, so here we have our two conservation laws. Conservation of momentum right here, and conservation of energy right here. So our first law says that the total momentum before, which is the momentum of this particle, which is m1 times v1, plus the momentum of this particle, which is m2 times v2, the initial momentum has to be equal to the momentum afterwards, which is m1 times u1 plus m2 times u2. And conservation of energy says that the total energy before, which is total kinetic energy before, is, okay, I've dropped the 1/2 because there's a half everywhere here, so we just multiply it. So m1 times v1 squared, that's the energy of this thing, actually twice the energy, and m2 times v2 squared, so that's the energy before, and then the energy afterwards, m1 u1 squared plus m2 u2 squared. Okay, so we have two equations in two unknowns, u1, u2, and we see it's not quite a linear system because this equation is quadratic while this equation is linear. So it may look like it's sort of falling outside linear algebra, but we'll see that that's not really the case. Let's take these two equations, let's call them 1 and 2, and let's just rewrite them slightly. So let's bring the m1 terms here to one side. So m1 times v1 minus u1, these two terms. And on this side we'll have m2 terms with u2 minus v2. And we'll do the same thing for this equation here. Bring the m1 terms to one side, so m1 times v1 squared minus u1 squared. And bring the m2 terms together, u2 squared minus v2 squared. And let's call those 3 and 4. So these are just rewrites of equations 1 and 2. And now let's take equation 4 and divide it by equation 3. So we'll take this expression divided by this expression, in which case the m's ones will cancel, and v1 squared minus u1 squared divided by v1 minus u1 is just v1 plus u1. And so that's going to be equal to this thing divided by this thing, which is similarly v2 plus u2. So this is a fundamental relation that's a consequence of these ones, and it's pleasantly also linear in u1, u2, v1, and v2. And it says that the initial plus the final velocities of particle 1 equals the initial plus the final velocity or speed of particle 2. And we'll call this equation 5. Well, now we have enough to solve for u1 and u2 because now we have actually two equations which are both linear in u1 and u2. So equation 3, which I've rewritten there, and equation 5, which I've rewritten there, can just be rewritten a little bit by bringing all the u1 and u2s to one side. So if we bring the u1s and u2s to one side, well, we're just recovering the initial equation that we started with called equation 1. So there's just the final momentum and equaling the initial momentum. And here we'll just bring the u1 minus u2 on one side equaling minus v1 plus v2 on the other side. And we'll think about this as being two equations in u1 and u2, with the other things as being constants which are given. Now, we could of course solve this just with high school algebra, but we've learned to organize ourselves here in linear algebra using matrices if we can, and vectors to organize systems of equations. That gives us more insight into what's going on. So let's do that. Let's rewrite this in a matrix form. The left-hand side here is really a vector, and we can write that as this matrix times the vector u1, u2. Because m1 u1 plus m2 u2 is that first term, and 1 times u1 minus 1 times u2 is that second one. And then we'll put these two numbers here in another vector. So we have matrix times unknown vector equals known vector. So we can solve for the unknown vector u1, u2 by multiplying by the inverse of this matrix. Sort of a nice way of doing it. And how do we find the inverse of this? Well, we divide by the determinant, which is minus m1 minus m2. So it's minus 1 over m1 plus m2. And then what happens to this when we invert it? Well, we have to change the diagonal elements. So that becomes minus 1 there and m1 there. And the off diagonal elements, you may recall, are multiplied by minus 1. So that's the inverse. This whole thing is the inverse of that matrix, which we're now going to multiply by this column vector. So to make it a little bit easier, let's just take that minus 1 and multiply it by this matrix. So we have a little bit nicer matrix there. And just 1 over m1 plus m2 there. Okay, so now when we do the matrix times vector, what we're going to get is 1 times this plus m2 times this. And please check that what you're going to get after you do that is m1 minus m2 times v1 plus 2m2 v2. And the second entry is 1 times this minus m1 times this. And again, just please check that I've done this right. We get 2m1 v1 plus the negative of this m2 minus m1 times v2. Now, notice something here, that the sum of the coefficients here, sum of the coefficients is m1 plus m2. And if we divide by m1 plus m2, then the sum of the coefficients is actually 1. So this is actually an expression that's telling us that u1 is a particular affine combination of v1 or v2. A convex linear combination, you may remember, when the coefficients add up to 1. But they're not necessarily between 0 and 1. Depends on the relative values of m1 and m2 here. And similarly here, it's the same story. They add up to altogether 1. So we're getting affine combinations of v1 and v2 in here. All right, so this is a complete, explicit resolution of our problem. If we know the initial velocities v1 and v2, and we know the masses m1 and m2, this is the formula that tells us what the two final velocities are, and we've computed it with just a little bit of linear algebra. Okay, so let's record this nice formula, this final velocity formula that tells us what the final velocities are in terms of the initial velocities and a matrix that's coming from the two masses, m1 and m2. And now I want to introduce a space-time diagram. It's going to be very important for us in physics, but it's already here in this relatively simple situation, instructive and useful, as we'll shortly see. What we want to do is we want to think about a particle moving along a line in terms of two coordinates. To describe this particle, we really need to know at any given time where it is and what time we're talking about. So there's really two coordinates that are involved for any position of the particle. So for example, here's our little particle, say of mass m, and at time t equals 0, it's at position -1, and it's moving in this direction. A little while later, 1 unit of time further on, it's moved to position 2. So we're assuming it's moving steadily in such a way that at every time period of 1, it will move 3 over. So we can represent the various events here by this space-time diagram, which has an x-axis, which is just like this axis here. So this is the space axis, representing our one-dimensional space on which things are moving. And this vertical axis is the time dimension, which is recording the time when various things are at certain positions. So the particle being here at time t equals 0 is corresponding to this point here on the space-time diagram. The point with x-coordinate -1 and t-coordinate 0. A little while later, when the particle's here, that's position x equals 2 and time t equals 1, so it's represented by this point here. So a point in this space-time diagram represents both a position and a time. And then the trajectory of the particle is described by this line that passes through these 2 points. And of course passes through many other points. So if we wanted to know where is this particle going to be at time t equals 2, we would say time t equals 2 and go over here and we would see that it's at position 5, say. And if we wanted to know, when was the particle at -2, so we'd go over here and say, oh, the time was probably something like a -1/3 or something. All right, this is called the world line of the particle, and it describes the complete history of this particle moving along through space and through time. Now, the slope of this line is obviously closely connected with the speed of this particle. The speed, v, is change in x divided by change in time. In this case, it's changes x3 in a time period of 1. So the velocity in this case is 3. And that's 1 over the slope of this line as we would usually see it if we were thinking of an x-y coordinates. Like in calculus, the slope of this line would be 1/3 because it would be delta y over delta x. Here we have delta x over delta t, so it's like the reciprocal of the usual slope story in calculus. So the more a line is like this, the faster the velocity is. The more the line is like this, the slower the velocity is. In an extreme case like a line like this, the position's not moving at all, so the velocity is in fact 0. And in the extreme case when this thing would be horizontal, well, that would correspond to sort of instantaneous or infinite velocity, which of course is not achievable. All right, so this is very familiar, I hope, to us as linear algebraists. Okay, we are working with physics here. It's very elementary physics, but there are really 2 quantities that are involved, the position and the time. And if there are 2 quantities involved, we know that we should be thinking about a 2-dimensional space. We don't have to worry about what does it mean. It's just that a 2-dimensional space is the mathematical construct that allows us to represent the situation in a good way. And this is in fact very useful to understand the motion along this one-dimensional line. All right, I want to now show you a picture or a diagram that illustrates this collision of 2 particles on a line. One particle coming this way, maybe another particle coming this way, and they come together and they collide elastically and then they bounce back. All right. So exactly the situation that we were talking about with initial velocities v1, v2, masses m1 and m2, and final velocities u1, u2. I want to picture that now in this space-time diagram. And we get an instructive, kind of pleasant geometrical configuration, which we might call a butterfly collision diagram. Let's call it that. All right, so what's going on here? Well, here is the x-axis, and here's the t-axis. All right. And here is time equals 1. And here's time equals -1. So this is the line when the time is always -1. This is the place where time equals 1. And let's suppose that we have 2 particles, one coming in from this direction, say, one coming in from this direction, and suppose that they're going to collide at the origin at 0.0 at exactly time t equals 0. So that's what's represented here. The world lines of these 2 particles are represented by these 2 lines. This is the world line of the particle that's, here's 0, that's moving towards 0 from the left, and this is the world line of the particle that's moving towards 0 from the right. This one's a little bit closer to horizontal, so it's faster. This particle is going faster, and this particle here is going a little bit slower. Okay, and they meet here at the origin, they collide elastically, and then they bounce back. So this one bounces back and heads off back where it came from, and this one also bounces back and heads off where it came from. And we can actually see the final and the initial velocities very clearly in this diagram. Where? Well, if we just look to see where the world lines meet this line t equals minus 1, and then these two where they meet the line t equals 1. This will be the point minus v1 minus 1. Why is that? Because this separation here is 1. All right. So if we actually calculate delta x from here to here, the change in x is 0 minus v1, that's v1, divided by 0 minus 1, that's 1. So the velocity that's associated with this is v1. Similarly, the velocity associated with this is exactly v2. So the velocities are recorded on this line t equals minus 1 by having x coordinate minus v1 and x coordinate minus v2. In a similar kind of way, once we have the particle bouncing back, here it's moving this direction here, and here's its world line. Wherever it meets the line t equals 1, say at the point u1, 1, right, then u1 is going to be the velocity of this particle represented by this world line. Why? Well, just because the velocity is the change in x divided by the change in t. And we've organized it so that the change of t is 1, and so the change in x is u1, because we're assuming that velocity is u1. And similarly, this one here meets the line t equals 1 at the point u2, 1. All right, so here are these two particles bump, and then they come out. These are the two world lines. Now there's some interesting sort of elementary geometry here that follows from the equations that we've derived. And the first one is that these two lines, the red ones, are in fact parallel. These two lines are parallel. So A1, B1 is parallel to A2, B2. Why is that? Well, what's the vector from this point to this point? It's obtained by taking the differences of the position vectors. So u1, 1 minus v1 minus 1 will be, first coordinate will be u1 plus v1, and the second coordinate will be 2. Similarly, the vector from here to here will be first coordinate u2 plus v2, second coordinate 2. But remember, equation 5 said that u1 plus v1 equals u2 plus v2. So these two vectors are exactly the same, and they're therefore parallel. So that's the first remark. The second remark is that since this line here is obviously the mid line between this line and this line, we have parallel lines here and they're equally separated by 1, it follows that this point here is the midpoint between these two. So we get it just by averaging the coordinates. Remember, the midpoint between 2 points in the plane is just obtained by taking the average of the x and the y coordinates. So the average of 1 and minus 1 is 0. Yes, as it should be. And the average of u1 and minus v1 is u1 minus v1 over 2. Similarly, this point here will be u2 minus v2 over 2. And now we make the observation that the equation 3 that we wrote down can be rewritten like this. The equation 3 was that m1 times u1 minus v1 equals minus m2 times u2 minus v2. So we just rearrange that by taking the two masses one over the other. Then we're going to get u2 minus v2 over u1 minus v1 with a minus sign somewhere. And what that is saying is that these positions, u1 minus v1 over 2 and u2 minus v2 over 2, are directly proportional to m1 and m2. So this coordinate here is actually some multiple of m1, say lambda times m1. And this coordinate will be minus lambda m2. In other words, this to this will be m1 to m2. So the masses are represented here by the relative sizes of these two segments, this one and this one. So in this particular situation, we can see that m1 is somewhat smaller than m2. All right, so maybe something like this. Here's m1 and here's m2, which is a little bit bigger. And m1 is represented by this world line, which is flatter, so faster than this one here. It's represented by a bigger v1 vector rather than this one. And then when they collide and head off in their respective directions, then their slopes look pretty similar, and we get u1 and u2. So this is kind of interesting because now we're in a position to geometrically solve this problem. So we had an algebraic solution before, but now we see that it's actually reflected in sort of pleasant geometry of this butterfly kind of configuration. Just remember that these lines are always parallel. This line is midway between this line and this line, and that the masses of these two particles are proportional to this segment and this segment. So this gives us a geometrical way of solving this kind of situation, even if we had perhaps forgotten the algebra. All right, so there's some interesting possibilities here for you to play around with and practice some physics at the same time as doing some pleasant elementary geometry with some simple diagrams. So to give you some practice, exercise number 1 is to make space-time butterfly collision diagrams to illustrate and predict the results of the following collisions. So this diagram is supposed to be meaning that we have a relatively big mass and a relatively small mass over here. And this relatively big mass has a velocity which is represented by this vector, basically going about twice as fast as that vector there. So we have a big, heavy particle going relatively fast and a smaller, lighter particle going much slower, and then they bump together. Okay? We want to know what happens. And I want you to actually draw this out on a space-time butterfly diagram and work out what happens. And this one here, well, we have two maybe more equal particles, with this one having a bigger vector of velocity than this one. Here we have a collision between two particles which are going in the same direction. The two particles don't have to be coming towards each other. So as long as, say, the one behind is going faster than the one in front, eventually it's going to catch up and they're going to collide and there will be some interaction. So here we have a more massive particle going faster, chasing a smaller particle going slower. And here we have a smaller particle going faster, chasing a slower particle that's going slower. Again, you can make diagrams and try to figure out geometrically what's happening. In the next exercise, we can also try to use these butterfly diagrams to find unknown masses and velocities, not necessarily the final two velocities, but we might have other pieces of the puzzle and we wanting to know, what's this initial mass or this initial velocity and so on. So for example here, suppose we have a mass m1 with a velocity given by the size of that vector, and then we have some unknown mass m2 with a velocity given by v2, which is roughly half of v1. And suppose that afterwards we know that m1 goes bouncing back with a relatively high velocity, almost twice as much as it came in at. Then can we figure out what this mass m2 is? And can we figure out what this the final velocity of m2 is. And similar kind of situation over here. We have a mass m2 coming in this way with some velocity. We have some unknown mass coming in this way with some unknown velocity v1. And we're told that this one, number 2, bounces back with the velocity u2, and this one bounces back with a velocity u1. Can we figure out what m1 and v1 are? All right, so our third exercise is in the same kind of direction, but a little bit more subtle. So are there conditions required on the 4 velocities, v1, v2, u1, and u2, to ensure that they can be input and output velocities of a collision? So if we're given 4 velocities, v1, v2, v3, v4, what kinds of conditions, if any, are required in order that they actually can be achievable by appropriate masses? In such a case, how do we solve for the masses m1 and m2? Both algebraically and geometrically. You might want to think about this problem from both directions. Of course, this whole thing is sort of scale invariant in the sense that if you multiply the masses m1 and m2 by 5, then essentially you're getting the same picture. So the masses are really only determined up to scale. It's really the proportion between the masses which is really the physically relevant quantity, because we can rescale things as we like. All right, so there's some, again, some more linear algebra floating around here, and something for you to think about. Finally, I think it's really necessary to ask this question. How do we know that the laws of conservation of energy and momentum actually hold? We've stated that they hold. How do we know that they do? Well, one answer, which is a relatively easy answer at some level, is because they are observed experimentally to hold. Okay, it's maybe not such an easy answer in the sense that a fair amount of work is involved. You can make lots of experiments and check that these laws actually empirically seem to hold over a wide variety of situations. It's probably also better, though, to look for a structural reason. So in physics, we don't want to just prove statements by saying, well, this is all because of experimental fact. Yes, occasionally we want to go to experiment, but we'd like to have the logic of the structure such that we minimize the need to go to experiment. And it's remarkable that another answer was really developed, and it's one of the great accomplishments of 20th century mathematics here. And it's a remarkable theorem of the great German mathematician Emmy Noether, who was the greatest female mathematician of all time. And she discovered that these conservation laws, in fact, are consequences of the symmetry of the equations of motion when you frame them in a sort of Lagrangian setting, in particular with respect to time and position. So it turns out that the conservation of energy is a consequence of the fact that the laws of motion are invariant with respect to time. If you change time, if you translate time, then the laws don't change. And that turns out to be the driver of the conservation of energy. And similarly, the fact that the laws of motion are unchanged if you translate. If you change the position by just translating it, the laws of physics look the same. So as a consequence of that symmetry with respect to translation, the law of conservation of momentum follows. So hers was a very general theory that explained not just this, but showed that in fact physicists could expect conservation laws in a wide variety of situations whenever there was some symmetry floating around. It was really a driver of the search for symmetry by physicists in the 20th century. Her theorem was, I think, published around 1918, which is roughly about the same time that Einstein's general theory of relativity came out, and the two both were very important sort of contributors to then subsequent developments of physics. In my opinion, this is the most important 20th century theorem of mathematics. Emmy Noether's theorem here It's absolutely fundamental importance, especially for modern physics. All right, so we've had this sort of light introduction. I hope you've enjoyed the geometry that we can naturally associate to momentum and energy, and particles bouncing around off each other. In our next video, we're going to take a big step forward, and we're going to try to move towards special relativity. I want to frame that subject perhaps in a somewhat novel way. And so I think we're going to have some interesting things to talk about with special relativity. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.